My name is Raul. I'm a scientist working in Germany, and for my scientific career I started in Venezuela back in the 2000s, early 2000s, in the study of physics and specialization on applied physics. In 2005 I had the chance to go to Paris, France, where I made my internship and later on my PhD on the application of atomic force microscopy for the investigation of nanoparticles. It was in Paris in this period where my journey into the nano world started. Right after my PhD thesis, I went to Kaunas, Lithuania, and this is also a very interesting work in my scientific career, since for the first time I realized of all the potential that arises when you couple atomic force microscopy with optical spectroscopy. This was my meet with nanolight. Later on, in 2011 and until now, I'm working in Germany in the Chemist University of Technology, and I'm interested in the development of atomic force microscopy and advanced atomic force microscopy methods, especially in combinations of AFM with optical spectroscopy, photoluminescence, optical absorption, and Raman spectroscopy also. This allows me, this period in chemics, allowed me to grow myself and also the research I'm doing to take nano to a completely whole new different level, which I hope I will be able to tell you something about. There are three main directions in which I'm focusing in Germany. They can be classified in these three parts. One of them, as I already mentioned to you, is a combination of atomic force microscopy with light, which gives rise to nano-optic applications, plasmonics, and photonics. The other two are concerned with materials. Materials-wise, I'm interested in carbon nanotubes, for example, in graphene oxide and graphene, and also in other kind of two-dimensional materials like gallium selenide or zinc sulfide, and even molybdenum disulfide. So this is an interesting combination because we develop methods that allow us to understand these materials at the nanoscale. And if you realize there are many materials that their properties change as a function of dimension, and we make the methods that allow to access this kind of information. Why is this important? Or from the nanomaterials, why are they so important? If you take into account, for example, one very important problem now in health sciences or in biomedicine also, is related to cancer research. And there are two particular problems here in cancer research. One is related to the selectivity that drugs have. You have chemotherapy drugs which are very efficient killing the cancers, tumors, the cancer cells, but unfortunately these drugs, they don't make a distinction between healthy tissue and cancer tissue. So they end up killing all in their way. And this is a very negative thing or a critical thing because the side effects of chemotherapy can be as bad as the cancer itself. And this is a consequence of the lack of selectivity of these drugs. The other very important question or problem in cancer research concerns the early detection of cancer, the early diagnosis. This is important because you will have the best chances of recovery from cancer when the diagnosis is done the earliest possible. So this is an example shown by these colleagues from China. They also show how to determine, how to apply plasmonic nanoparticles. In this particular case, is tags, is materials that will allow to make diagnosis of tumors. The way they work is you have a cancer cell, you have these nanomaterials, they will functionalize externally with a group of molecules that will selectively interact with cancer cells. These cancer cells, they have the overexpression of some molecular groups, and this is the kind of groups that this nanoparticle system are functionalized to react with. Once you do that, one of the demonstrations that they show is in an animal system, in mice. They inject or they induce a tumor in these mice, and they inject this nanoparticle system for detection. And you can clearly see that when you don't have a target system, like in the right side, then all of the nanoparticles of most of these nanoparticle systems will end up in the liver. That's what happens when the system, the body of these mice recognizes something external, they will put it as excrete in the liver. What happens also is that if you have a target system, as they show here, most of the particles will end up in the tumor side. As can show here, you have the signal coming from the Raman probe, the Raman tag attached to the nanoparticle system. So also the interesting part is not the selectivity that I mentioned to you before, that can be used or exploited as a drug delivery system, but also you have the diagnosis component there, since you can use this nanoparticle system to track where the tumor is, the localization of this tumor. And this method of detecting this tumor is based on optical spectroscopy. You have a Raman spectrometer which is working near infrared wavelengths, and this is an important wavelength of light or spectral range of light, since most tissue, animal tissue and human tissue, is transparent at this wavelength, so we can sense inside your tissue without the need of cutting or without the need of being invasive. So this is also a very important point. One of the critical aspects of this research, beyond the proof of principles that you make or research make in the lab, is the possibility or to scale up and to have an optimized system that can be used in human patients and can become a routine method of treatment and also diagnosis. Now, to make this a reality, to take it from the lab to the real life applications, you need to be very careful and to understand very well how is the interaction going on between the nanoparticle system and the different functional groups that you're using to function as your nanoparticles. How the environment affects this functionalization, how the chemical reactivity of the nanoparticle or the difference of the coating layers will change under different environments. All these are important questions that are very desirable to determine at the nanoscale. Now, you may be able to, or you may be naively think that if you want to understand or to see this kind of nanoparticles, then you can simply use an optical microscope. Now, an optical microscope has a wide range of applications, like from biomedicine, bioanalytics, material science, and so on. It's very, very important, optical microscope. But as in any conventional optical system, like telescope or any optical microscope, the spatial resolution or the smallest objects you can see will be limited by what is called Ab's diffraction limit. What it says is the following, is that the distance or the size of the objects you can see will be limited by the wavelength of light you're using and by NA, divided by 2 times NA. NA is the numerical aperture of the optical system. So this is called as the Rayleigh criterion also. This size is the Rayleigh criterion. If you have particles that are separated by distances smaller than that, you will not be able to distinguish them. So if you're very ambitious with the optical microscope, then you want to get the most powerful system with the best magnification, and one way to have the best magnification is to decrease, for example, the numerical aperture, to increase the numerical aperture or to decrease the lambda. But lambda, usually you want to work in the visible range or near infrared range, so you don't have much of a flexibility there. But what you can also do is to increase the numerical aperture, and one of the highest numerical aperture that can be objectives, for example, that can be used in an optical microscope is about 1.4 for oil immersed or water immersed objectives. If you take into account some numbers, for example, the wavelength of light is 500 nanometers, and if you consider the numerical aperture of 1.4, you will come up to 250 nanometers of spatial resolution. Now, this is a very decent number. This is very good. For example, if you're interested in cells, which are of a couple of micrometers up to hundreds of micrometers, it's not a big deal to have social resolution of 250 nanometers. Actually, this is a very good resolution for such large system. However, if you're interested, as I mentioned before, in nanomaterials, where you're interested to see even below 20 nanometers, this is not going to cut it. The optical microscope is not enough. Consider, for example, organic nano-objects like DNA or even carbon nanotubes, which have a diameter of a couple of nanometers. No chance that you can use an optical microscope to distinguish between 2 different DNA strands when they're very close together, or even different carbon nanotubes to visualize them. That's not just possible due to this diffraction limitation of optical microscopy, and it also affects optical spectroscopy. So these questions are important because, or how to take optical microscopy imaging to the nanoscale, because it will allow you to answer questions such as what is the material you're working on. This allows you also to determine its function, for example, in biomaterials or different components of a cell. What is these components, what do they do, what is the responsibility of this part of the cell. Also, it will allow you to tell what is the spatial location, which parts in your system is this different from the others, so you need to distinguish, especially at the nanoscale list. And of course, you will also like to know what is the chemical composition of these different materials and where everything is, the spatial location, the function, and the chemical composition, for example. These are questions that, to demonstrate or to illustrate how relevant these questions are, consider that in this century, at least 6 Nobel Prizes have been awarded to people, to researchers who have, in one way or another, addressed one of these questions. One representative example is the Nobel Prize in Chemistry in 2014, which was attributed to the developers of super-resolution microscopy, in particular stimulated emission depletion, which allows to take a conventional fluorescence microscopy from the micrometer scale diffraction limit beyond what is allowed by the diffraction limit at the nanoscale level. This is illustrated by this image that we have there. It's exactly the same as like chromophore dispersed on a substrate, and you can see in the confocal image how large they look like. It's because they are amplified, they are convoluted with the spread point function of your optical system, so you will see a very large agglomerate. While in reality, if you have a very good spatial resolution like STID, you can clearly see all these small points that you see in this image. If you zoom in, you will see that you can actually resolve and visualize a single chromophore. This is an illustration of how you can access information that is simply not possible to access using conventional optical microscope. For example, the shape that this chromophore has. There is another kind of material, of methods, another class of technology that allows to visualize objects with nanoscale resolution. This is what I call collectively as scanning pore microscopy. And the principle of how it works is very similar, and I would say it's universal. You have a sample and you have a probe. This probe can be a very sharp tip, for example, and what you're interested is the interaction that arises between this tip and sample. You profit from this tip-sample interaction in order to control the position between tip and sample, so that you can move the tip or the sample one with respect to the other in a pixel by pixel, point by point, and knowing one of these parameters of interaction, you can use it to control the tip-sample distance and to make a three-dimensional map of your system. So there are different parameters. For example, if you're interested in atomic force microscope, the parameter that is used to map the topography of the sample is a mechanical interaction, or between the tip and the sample. Also, in scanning tunneling microscopy, for example, or scanning electrochemical microscopy, the parameter in tip and sample in the tip-sample interaction that you're interested on is the current. So you follow this current, and you use this as a parameter to control the tip-sample distance. The particular example of STM is very illustrative. What happens here is that you need a metallic tip and you need a metallic substrate. If you apply a potential difference between these two, and of course if they are not touching, classically you will not expect to measure any current since they are not in mechanical contact. But quantum mechanically, there is a non-zero probability that electrons will flow from the tip to the sample. Now, this current and the nature of this current, which is strongly dependent with the tip-sample distance, is what allows STM to provide, or the capability to produce images at the atomic level. Is that it depends exponentially with the distance. So what you see here is a current in tip-sample current that depends exponentially with distance. There is an epsilon inside, and this epsilon depends on the work function of the materials. The operational principle is very simple. What you do is that you define a given operation or set point current. So the system, what it does is you tell the system, move the tip sample distance in order to keep this tip sample current constant. So what it does is you will have a point in your sample surface, you will move it pixel by pixel to another point, and if the system detects a change in current, it will adapt or it will tune the tip sample distance in order to come back to the preset or selected tip sample current. So let's consider if you have some vacancies, if you have some atoms missing in your surface, then when the tip goes to that region, there are some missing atoms, so the current will decrease because there's nothing there. Then the AFM electronics, or the STM electronics, will react to this change by approaching the tip sample, the tip to the sample even more. Contrary, the way if you have, let's say, an aggregate of metal atoms on a surface, when the tip goes and hits those aggregates, the tip sample distance will be much smaller, then the current will increase, and the system will react to this increasing current by pulling the tip up, or the sample down. So this is basically the same principle as almost any scanning for microscopy works. You have a parameter that you follow, or the electronics follow this parameter, and if there is any change in the height, the tip sample distance will be adapted in order to bring to the initial, previously determined set point. So it can be the deflection, it can be the current, it can be the electrostatic force, for example. One of the most representative examples of the application of scanning toning microscope was precisely the first, one of the first papers on this, and it's a demonstration of the reconstruction of silicon 111. In this time, it was a very, very high topic to find out or to provide an experimental demonstration of how this reconstruction occurs. And these guys, the inventors of STM, did actually that. They used STM to map with atomic resolution the silicon 111 and to confirm the 7x7 reconstruction. Precisely this work was the one that a few years later, the reason why these guys got the Nobel Prize because of the design of the scanning toning microscope. Now, STM has evolved since these early 80s, and until now, it allows to do something that before was considered like magic in science fiction. And this is a possibility and capability to manipulate matter at the atomic level, to move atom by atom and make any arbitrary patterns. For example, these OU letters that you see in this figure. This is also possible when you operate STM under particular conditions like ultra high vacuum and also low temperature, when you need this mechanical stability to be able to have this control. But this is also an illustration that scanning for microscope is not only a passive method that allows you to visualize something, it also allows you to modify, to go and manipulate matter at a very, very atomic level. One of the reasons why scanning for microscope has achieved the level, the development, the high development that is achieved until now is thanks to the existence of this kind of materials, which are called piezoelectrics. Piezoelectrics have the interesting property that when you apply a potential difference in this material, there will be a deformation as a response to this potential difference. And this is very precise. This allows the movement or the motion of the tip or the sample in a sub-nanometer scale. For example, this is a piezoelectric tube. It's a classical architecture for an STM, for example, when you want to have very small movement with a very high precision. You have a piezoelectric tube, and you have different contacts in different sides, so that if you apply a potential difference between this one and this one, for example, the tube will deform in this direction. And it will happen, of course, the same if you apply a potential difference in the other opposite directions. So that if you have a tip at the end of your piezoelectric tube, a cantilever or a STM tip, you can use this by applying this potential. You can use to scan the tip on the sample. And also, of course, you can have a stacked tube on the vertical axis to apply a potential difference in that axis to control the tip sample distance. And I mentioned to you before, for example, in the case of STM, that you have the current that the system tries to keep constant all the time. So this is your set point parameter using the feedback loop. Now, how the system reacts, or what the system does if it recognizes that there is a change in current, it will apply a potential to the piezoelectric tube in order to either decrease or increase, depending on how the current changes, the tip sample distance. And this is one of the most important components of any scanning for microscopy method until now. There is another class of SPM, which is called atomic force microscope, and it, like any other SPM, it works in a relatively slow way, which is scanning pixel by pixel, one pixel at a time, one line at a time. So you make a raster scanning of the whole image, and you make a construction of it, for example, a 3D topography point by point. The first time I discovered or that I witnessed how AFM worked, I saw it by myself. I was kind of disappointed because I read about it, but something that people didn't mention is how long time it usually can take to obtain an image. I mean, if you have an optical microscope, you just take your sample, you put it on the stage, you focus, and you have your image at once. In atomic force microscope, it's not so fast. You require some minutes depending on the pixel size that you have and depending on the scanning speed that you can go. However, this initial disappointment was completely overcome by the realization of what potential atomic force microscopy offers. That is it rivals or is completely different and complementary to the optical microscopy. The way atomic force microscopy works is similar to STM. You have a very sharp tip, but contrary to STM, you're not measuring currents. What you're measuring are interactions. So the interaction between the tip and the sample, for example, in this case, will be enhanced or detected thanks to the force that it makes on the cantilever. So the force on the tip will induce a deflection of the cantilever. So the cantilever in AFM is a force sensor. The way we follow the deflection of the cantilever using what is called the optical lever system. What it does is you have a laser that reflects on the back of the cantilever, then a mirror, and then goes to a photodetector. So that very small changes in the photodetector, in the cantilever, up to 0.5 nanometers, for example, you can amplify using the optical lever system up to millimeters that you can easily detect in a photodetector. Now, conventional methods that are used, for example, to investigate nanoparticles or electron microscopy, in this case is an interesting example since you have an iron oxide nanoparticle that shows different morphologies. For example, you see some hexagon plates there. You see also some rhomboidal particles, some things that seem a bit rectangular particles, or a bit more cubic or spheroids. So you have a zoology of different shapes that you can see in the high resolution microscopy. If you have the same nanoparticle system visualized in atomic force microscopy, you will obtain the following images. You have this 3D information of your sample, and this is very important because, for example, here it allowed to end with something that was, until this moment, a conflict in the literature, something that was not very clear. What is the real morphology of this kind of nanoparticles? Atomic force microscopy allowed to determine that the actual morphology of the nanoparticle is more like this one that you see here. It's more like a lozenge. But there is no such thing as hexagonal nanoparticles or spherical nanoparticles or rectangular nanoparticles now. AFM shows that the only morphology that you have there is rhomboidal. Atomic force microscopy was also developed by the same people who developed the STM. And precisely, or coincidentally, it was in the year 1986, which was the year when these guys obtained the Nobel Prize thanks to the development of STM. The way atomic force microscope works, there are two ways, or two typical ways. One is called contact mode, in which your tip is in constant contact, mechanical contact with your sample, and it scans pixel by pixel, line by line, as I explained before. The disadvantage of this method is that you will have some strong force. The force is continuous on the sample, so that if you have a material that is very soft, you can deform it. Or if you have material that is not very well attached on your substrate, then what you will have is you're dragging around the material. It will be hard to study, to analyze using this method. One of the positive things about the contact mode is that it's very easy to implement. And under liquid conditions, as you will see later on, you can also minimize these shear forces. However, there is another method or another way of operating atomic force microscopy, which is called tapping mode. This is also called as amplitude modulation, atomic force microscopy, intermittent contact, atomic force microscopy, oscillatory or AC mode atomic force microscopy. So there are different ways to know this method, which I will call it here tapping mode. What tapping mode does is that you have the tip, and the cantilever makes the oscillation of the tip at that given frequency. This frequency is set externally by a piezoelectric, and usually we choose a resonance frequency of the mechanical system of the cantilever. So we heat it in such a way that it will be very sensitive to changes in the amplitude also. The advantage of tapping mode with respect to contact mode is that since there is only intermittent contact with the sample at each oscillation cycle of the FM motion, then the shear forces will be highly minimized. This is a very important point because now you will be able to visualize or to analyze samples that are very soft, even liquids you can analyze using atomic force microscopy in the tapping mode. Now, one way to understand or to describe how dynamic atomic force microscopy or tapping mode AFM works is by using what we call the Swiss knife of physicists, is to model the system as an harmonic oscillator. This is the equation of motion of this system is a nonlinear second-order differential equation, and you could identify some terms here, like these two terms, define what's called Hooke's law. It means that there is a force in the cantilever system or the spring system. When there is a deflection, this force will be proportional to the spring constant or the stiffness of the cantilever times the deflection or the deformation of the system at its equilibrium. The second part is a dissipative force. You can identify that because it's proportional to the velocity of the system, and this is due to the damping the cantilever experience when due to the interaction with molecules, for example, or in liquid if you do make it on liquid. The second term, the other term that you see here is the external excitation that you apply to the cantilever at the mechanical frequency of the system in order to make it oscillate. In the last term that you see here is very, very important. This is called deep sample interaction. And in a very approximate way, we can describe this deep sample interaction as being composed of different terms. The first one is a long-range interaction described by a van der Waals force. It's a van der Waals force. You can also have some repulsive interactions or contact interactions that are composed of addition, that depends on the surface energy of the system, and also a repulsive force, which is dependent on the elastic properties of the system. This addition force is actually a negative at the end because the surface energy is negative. So here you will have an attractive force. You have an attractive force and a repulsive force in the contact regime. There are other forces that I don't mention here, but already this model, simplistic model, can allow you to model your deep sample system in a very good way. Or however, if you want a more realistic approach, you also need to consider capillary forces, for example, or you also need to consider electrostatic forces. Contact mode AFM, in this particular case, when you operate it in liquid, can give very good results. What you see here is a sort of atomic force microscopy image of different membrane proteins, and you can even see, like you see in this panel here, is the possibility to visualize live in operation. What you see is the opening and closing of ion channels of a membrane in reaction to different response due to the pH, for example, of the system. You have from pH 6 when you have the pore is more or less closed, and you increase it to 7.6 pH, and then this pore opens. So this is a beautiful application on how atomic force microscopy allows you to visualize such kind of system with such incredible resolution. You can see the scale bar here is 2 nanometers, and each of these units is a single membrane, a single protein. Membrane protein. So you have a very impressive spatial resolution that you can also allows you to visualize materials, biomaterials particularly in the pristine conditions, like in particular conditions that mimic the environmental conditions they have in the body, for example, in native conditions. But however, there is a limitation here, is that you can see there is a color scale, it's a gray color scale. You don't see where different components or different compositional components, or you only see morphological changes. There's no chemistry information. And this is one of the largest limitations that atomic force microscopy has. So if you're as ambitious as I am very much like all the power that atomic force microscopy has, but this chemical limitation is something that I cannot just live with it. So I have worked for several years in trying to overcome this limitation of atomic force microscopy by providing it with a chemical sensitivity capability. One way to do so, and which I can illustrate this, is by the exploitation of a property or a kind of particles called plasmons. Plasmons occur, or plasmons in this case, or in this system, you have a gold tip in a gold substrate, and what you see here is the electrostatic or the electric field magnitude in a color scale. So the incidence electric field has a value of 1 volt per meter. You can see that the electric field can go as high as 1.4, 100 times more. So you have a concentration of the electric field between the apex, an amplification, and a spatial confinement. And this is the beauty of plasmonics, and particularly of tip-enhanced nano-optics, is that it allows you two things: amplification of the electromagnetic field and the spatial localization. So that this, if you see this 10 nanometers tip, and you have a localization of this high confined light in a location much smaller than 10 nanometers. So this confinement acts also as a localized light source. So suddenly you're not limited anymore by the diffraction limit of light, which imposes for similar wavelengths a spot size of 250 nanometers. Here you have a spot light source that is smaller than 10 nanometers. So that possibility to confine light and to amplify light is the one that makes this kind of images possible. What you see here is a complicated sample because its compositionally is very similar. This is all the components that are there, or carbon nanomaterials. You have graphene oxide in green color. In red, these wires that you see there, these are carbon nanotubes. And you have some spots around the part of this of the blue color. These are fullerenes, small aggregates of fullerenes. How can I give them colors, compositional colors? The way you can do that is because I have the fingerprint capabilities of Raman spectroscopy. So at each pixel of this image, I don't obtain only the topography in 3 dimensions of the system, I also obtain chemical information. I obtain a 4-dimensional map, or what is called also a paraspectral mapping, is that at each pixel I also have a full spectrum. So how we obtain that image is that I just take the intensity of this band, which is related to the 2D band of the carbon nanotubes, and I can see it in red there how the carbon nanotubes pop up. If I do the same with the D band of graphene oxide, you will see how clearly it illustrates where this graphene oxide is. And I do similar also with the fullerenes, and this C5 mode vibration of the fullerene make it look like the small aggregates that you see there, or the small aggregates that are everywhere around the surface. So this is the capability that coupling optics at the nanoscale with an atomic force microscopy can give. You have the spatial localization, the amplification, and the chemical fingerprinting that gives optical spectroscopy. In this case, Raman spectroscopy. These works, most of these works also have been realized in the semiconductor physics group of the Chemnitz University of Technology. Here is a picture of the group. This is the professor, the head of the group, Professor Dietrich San. And this is a picture of the group that, or the subgroup or the team that I'm responsible of. And this was a fascinating time since my time in Germany here since 2011. I started with a single PhD student, and now the team grew up to about 20 persons, from PhD, master, bachelor students, up to postdocs. And we have lucky enough, thanks to all these people, we have achieved scientifically something very good. We are one of the most scientifically productive groups in the whole Institute of Physics. And about half of the publications, for example, or the conference participation of the whole group is also represented by this group that I started from one single person and now into that. And it's not only because of me, mainly it's because of the passion that all these people have for the research I just talked to you about. So my ambition now is that hopefully with the information I gave you, it will spark some curiosity that will make you look for more information on the internet, or to get some books or get some papers and to find out more. I hope that I will have sparked this curiosity on you. If I did that, then my job was done here in this first lecture. Also, if you have any questions, I will be very thankful if you go either to our website and you can check out the things that we were doing. You can also see the publications that we have and the research that is going on. Also, like activities, conferences that we're organizing, as well as group members. Also, my email is there in the contact. If you have any question, any doubt, or any comment regarding this lecture or other lectures that will come, please, I will be very happy to hear from you. And with this, and in advance, I will thank you for all the questions that you will pass me. Thank you.